The universe is vast, dark, and mostly empty, but it isn't silent. Every so often it sends us a message, not in words but in stone and ice. A traveler from a distant, unknown star system has just entered our cosmic neighborhood. It's a giant, far larger than any we've seen before, and it's moving with incredible speed. This visitor, now named 3I/Atlas, has journeyed for millions, perhaps billions of years, through the cold, lonely expanse between the stars. It carries with it the secrets of its birthplace, a place we can only dream of. Its arrival is a reminder that our solar system is not an island, but a small part of a much larger galactic community of stars, planets, and wandering objects. This is a moment of profound discovery. Imagine a bottle cast into a cosmic ocean, finally washing ashore on our little island of a solar system. What message does it contain? What can it tell us about the shores from which it was launched? 3I/Atlas is that bottle. It's a pristine sample from another star's planetary system, a time capsule that has preserved the chemical ingredients of a world completely alien to our own. This isn't just another rock in space, it's a direct link to another part of the Milky Way, a tangible piece of another world that has come to us. Its journey through the interstellar void is almost unimaginable, a testament to the grand, slow dance of the cosmos itself. For most of human history, we believed everything in the sky belonged to our solar system. The planets, the comets, the asteroids, they were all ours, gravitationally bound to our sun. We were a self-contained family, but now we know better. The cosmos is not a series of isolated islands. It's a dynamic, interconnected place where material is exchanged between star systems. 3I/Atlas is the third confirmed proof of this incredible reality. It forces us to update our understanding of the universe and our place within it. We are not alone, at least not in the sense of being isolated. The galaxy is a busy place, and occasionally its traffic passes right through our front yard. This visitor challenges us to look up and wonder. It invites us to ask bigger questions. Are the building blocks of life common throughout the galaxy? Are other solar systems like ours or wildly different? 3I/Atlas offers us a rare, fleeting opportunity to find some answers. As it streaks through our solar system, every telescope we can point at it becomes a tool of interstellar archaeology. We are digging into the past, not of our world, but of another. This is exploration in its purest form. We don't have to go to the stars because right now, a piece of the stars has come to us, and we must listen to the story it has to tell. Before 3I/Atlas, there were others. They were the pioneers, the first whispers from the great beyond that forever changed our perspective. The first was Oumuamua, a name that means scout in Hawaiian. Discovered in 2017, it was bizarre. It was small, shaped perhaps like a cigar or a pancake, and it tumbled end over end. Most strangely, it accelerated away from the sun without any visible tail of gas, defying our expectations for a comet. Oumuamua was a cosmic enigma, a puzzle that sparked intense debate. Was it a new kind of object, a nitrogen iceberg, or something more? It left us with more questions than answers, a tantalizing glimpse of the strangeness the universe has to offer. Then, just 2 years later, came 2I/Borisov. This visitor was more familiar, yet no less extraordinary. Unlike Oumuamua, Borisov looked and acted like a comet. It had a fuzzy coma and a long, beautiful tail of gas and dust, formed as the sun's heat vaporized its icy surface. It was the first time we could clearly see that other star systems produce comets much like our own. By studying the light from its tail, we could analyze its chemical composition. We found chemicals that are common in our own comets, but also some intriguing differences. Borisov was a confirmation that the basic chemistry for building worlds might be universal, yet with local variations. These two previous visitors set the stage for 3I/Atlas. Oumuamua showed us that interstellar objects could be profoundly weird, challenging our very definitions. Borisov showed us they could also be comfortingly familiar, reinforcing our models of planet formation. Together, they opened a new field of astronomy. We were no longer just studying our own backyard. We became cosmic immigration officers, watching for travelers crossing our border. The discovery of these objects proved that they weren't impossibly rare events. They were just difficult to spot with our existing technology. We learned to look for them, to recognize their unique signatures. Now, 3I/Atlas arrives as the third and most spectacular messenger. It combines the mystery of Oumuamua with the observable nature of Borisov, but on a much grander scale. It's a giant, far larger than its predecessors, giving our telescopes a much better target. Its arrival confirms that our galaxy is teeming with these wandering bodies. Ejected from their home systems by gravitational tugs of war, each one is a unique data point, a piece of a galactic puzzle. Oumuamua was the strange scout, Borisov was the familiar cousin, and now 3I/Atlas is the magnificent ambassador, here to give us an unprecedented look into the heart of another star system. The discovery of 3I/Atlas was a triumph of modern astronomy, a testament to the power of automated sky surveys. It was found by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey based in Hawaii. ATLAS isn't designed to look for interstellar visitors specifically. Its primary job is to scan the entire night sky every few nights, searching for near-Earth asteroids that could pose a potential threat. It's our planetary defense system, a silent guardian watching for incoming dangers. On a routine night in late 2024, the system flagged a faint, fast-moving speck of light that didn't belong. It was an anomaly, an object whose path didn't make sense. At first, it was just another string of letters and numbers in a database, an object of minor interest. But as astronomers around the world began tracking it, a startling picture emerged. They calculated its orbit, tracing its path backward and forward in time. Standard comets and asteroids follow elliptical or oval-shaped paths around our sun. They are members of our solar system, gravitationally bound to it. But this object's path was different. It was on a hyperbolic trajectory, an open-ended curve that clearly indicated it came from far beyond our sun's gravitational grasp. It was moving too fast to be captured. It was a visitor, just passing through. The Minor Planet Center, the official body for these classifications, acted quickly. After confirming the calculations from multiple observatories, they gave it the designation 3I, with the I standing for interstellar. This was only the third time in history such a designation had been given. The name Atlas honors the survey that first spotted it, a fitting tribute to the robotic eyes that first caught our glimpse of this cosmic wanderer. The classification was a monumental moment for the scientific community. It meant we had another chance, another precious opportunity to study a piece of another star system up close, without ever leaving our own. The uniqueness of its trajectory is what makes it so special. Imagine throwing a ball so hard it escapes Earth's gravity and flies off into space forever. That's essentially what 3I/Atlas is doing to our solar system. It entered with so much excess energy, so much velocity, that the sun's immense gravity can only bend its path. It cannot capture it. This high speed is the smoking gun, the undeniable proof of its interstellar origin. It didn't form here. It has been traveling for eons, a lonely nomad, and for a brief moment in cosmic time, its path has intersected with ours, giving us a front-row seat to a spectacle from another world. What makes 3I/Atlas so fascinating to scientists is its sheer scale and unusual characteristics. Initial observations suggest it is enormous, possibly up to 10 kilometers in diameter. This would make it significantly larger than both Oumuamua, which was estimated to be a few hundred meters long, and Borisov, which was about a kilometer across. A body of this size is a true relic, likely a planetesimal, a building block of a planet, that was ejected from its nascent solar system during a period of violent gravitational instability. Its size means it has more material for us to study, and a greater chance of having preserved its original composition from the cold depths of interstellar space. Its structure is also a subject of intense interest. Unlike the comets from our own Oort cloud, which have spent billions of years in a relatively stable deep freeze, 3I/Atlas has endured a much harsher journey. It has been exposed to the radiation of the interstellar medium for millions of years. This long exposure may have created a thick, dark, and tough outer crust. Early observations show it is very dark, reflecting very little sunlight, which suggests a surface rich in complex organic molecules or carbon-based compounds. This dark crust might be protecting a more pristine, icy interior, a core that still holds the original secrets of its formation. Then, there is its speed. 3I/Atlas is hurtling through our solar system at a staggering velocity of over 150,000 kilometers per hour relative to the Sun. This speed is far beyond the escape velocity of our solar system, confirming its status as an unbound object. This incredible momentum is a gift from its parent star, and the gravitational chaos that flung it into the void. Its speed presents a challenge for observation, as it will not linger for long. But it also provides clues. By precisely measuring its velocity and trajectory, astronomers can work backward to try and identify the region of the sky, and perhaps even the star system, from which it originated. These features, its massive size, its dark and potentially crusted structure, and its incredible speed, combine to make 3I Atlas a scientific treasure trove. Its size means it will likely become very active as it nears the sun, releasing large amounts of gas and dust from its interior. This activity will give us an unprecedented opportunity to use spectroscopy to analyze its chemical makeup. We can search for water, carbon monoxide, and perhaps even complex organic molecules that are the precursors to life. 3I Atlas isn't just a rock, it's a dynamic, evolving laboratory that has traveled across the galaxy to perform for our telescopes. One of the most exciting quests in modern astronomy is tracing an interstellar object back to its home. For 3I Atlas, this cosmic detective story has already begun. Astronomers are using its precise trajectory and velocity, combined with vast star catalogs like the one from the Gaia Space Observatory, to rewind its journey. They are looking for a star system that it might have passed close to millions of years ago, a system that could have been its birthplace. This is an incredibly complex task. The galaxy is a swirling, dynamic place, and stars are not stationary. We have to account for the motion of every star over millions of years. Several theories about its origin are already being explored. One leading hypothesis is that 3I Atlas was ejected from a young star system that was still in the chaotic process of forming planets. In these early systems, gravitational interactions are fierce. Giant planets like our Jupiter migrate and can easily fling smaller bodies like planetesimals out into interstellar space. If this is the case, studying 3I Atlas is like studying a fossil from the birth of another solar system. It could tell us whether the processes that formed our own planets are common or rare throughout the galaxy. Another possibility is that it came from a binary star system, where two stars orbit each other. These systems are known to be gravitationally unstable environments, making them very effective at ejecting comets and asteroids from their planetary disks. A close pass by the companion star could provide the extra gravitational kick needed to send an object like 3I Atlas on its interstellar voyage. Finding its parent star system would be a monumental achievement. It would allow us to study the star itself and compare its properties to the chemical composition of the visitor it sent us, creating a direct link between a star and its ejected material. The chemical makeup of 3I Atlas is our most important clue. As it gets closer to the sun, the ice on its surface will turn to gas, creating a coma and tail that we can analyze with our spectrographs. We will look for the ratios of different elements and isotopes. For example, the ratio of deuterium, a heavy form of hydrogen, to regular hydrogen in water, can be a fingerprint of where in a protoplanetary disk an object formed. By comparing these ratios to those in our own solar system's comets, we can start to piece together the story of its home environment. Was it a water-rich system like ours? Or did it form in a place with a very different chemical recipe? The study of interstellar objects like 3I Atlas is fundamentally important because it allows us to sample the universe beyond our solar system directly. For centuries, our knowledge of other stars has been limited to the light they send us. We can analyze that light to learn about a star's temperature, mass, and chemical composition, but we can't learn about the planets or comets orbiting it in detail. These interstellar visitors are physical samples delivered right to our doorstep. They are pieces of other worlds that we can touch with our instruments. This is a revolutionary shift in our ability to conduct galactic science. These objects provide a crucial test for our theories of planet formation. We have detailed models of how our own solar system formed from a swirling disk of gas and dust. But is our solar system typical, or is it an outlier? By studying the composition of planetesimals from other star systems, we can see if they are made of the same stuff as our own asteroids and comets. If they are, it suggests that the chemical ingredients and processes for building planets are universal. If they are different, it could reveal a diversity of planetary systems far greater than we ever imagined, with different chemistries leading to different kinds of worlds. Furthermore, these visitors are central to the idea of panspermia, the theory that life, or its basic building blocks, can be transported between star systems. We are not suggesting that 3I Atlas is carrying living organisms. However, it might be carrying complex organic molecules, the amino acids and hydrocarbons that are the precursors to life as we know it. If we find such molecules on 3I Atlas, it would provide strong evidence that these essential ingredients can survive the harsh journey through interstellar space. It would mean that the raw materials for life could be delivered from one star system to another, seeding young planets across the galaxy. Ultimately, the importance of studying 3I Atlas lies in our innate human curiosity, our drive to understand our place in the cosmos. Every new discovery pushes the boundaries of our knowledge and forces us to reconsider what we thought we knew. These objects remind us that the universe is not a static backdrop but a living, breathing, and evolving entity. They connect us to the grander galactic story. We are not just inhabitants of Earth or even the solar system, we are citizens of the Milky Way galaxy, and these interstellar travelers are emissaries from our distant, unseen neighbors, inviting us to learn more about the vast cosmic family to which we belong. As this magnificent object continues its journey through our solar system, it's natural to feel a sense of awe, and perhaps a little apprehension. So let's be clear, 3I Atlas poses absolutely no threat to Earth. Its trajectory is well understood, and its closest approach to our planet will still be many millions of kilometers away, far beyond the orbit of the Moon. We are perfectly safe. We get to enjoy the scientific spectacle from a very secure distance. This isn't a disaster movie. It's a once-in-a-generation opportunity for pure discovery, a chance to observe and learn without any fear for our own safety. So, how are we studying it? Every major telescope on Earth and in space, from the Hubble Space Telescope to the James Webb Space Telescope, will be turning its gaze toward 3I Atlas as it makes its closest approach to the Sun. Astronomers will use spectroscopy to break down the light from its coma and tail into a rainbow of colors, revealing the chemical fingerprints of the gases it releases. Radar observatories might be able to bounce signals off its nucleus to get a better sense of its size, shape, and rotation. Every photon of light, every radio wave we can collect, is a precious piece of data that will help us unravel its mysteries. Of course, with an object this strange and wonderful, there will always be speculation. Could it be an alien probe? This is the so-called technosignature hypothesis. While it's an exciting idea, the evidence so far points overwhelmingly to 3I Atlas being a natural object. Its behavior, though magnificent, is consistent with that of a very large, active, comet-like body. Scientists must follow the evidence, and the evidence points to a natural origin. However, science remains open-minded. Radio telescopes will listen intently for any non-natural signals, just in case. The chances are infinitesimally small, but the search itself is part of the scientific process. As 3I Atlas swings around the Sun and begins its long journey back out into the interstellar void, what will we have learned? We hope to have a detailed chemical inventory of a building block from another star system. We may have clues to its parent star, and a better understanding of the diversity of planetary systems. But like Oumuamua before it, 3I Atlas may leave us with more questions than answers, and that is the beauty of science. Every discovery opens up new avenues of inquiry. After it leaves our sight, it will travel for millions more years, a silent messenger, heading for another distant star. And we will be left to wonder, how many more are out there? What new secrets will the next visitor bring? The universe has spoken, and our journey is to learn its language.